Hello everyone, and welcome to today's webinar in the CERDUP and ESTCP webinar series. My name is Rula Deeb. I'm a principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDUP and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of CERDUP and ESTCP by Dr. Herb Nelson, followed by a list of upcoming webinars in the webinar series. After Herb's opening remarks, we will transition to the technical portion of the webinar. Today's event features 3 presentations on the Land-Based Munitions Response Program Closeout. First, Mr. David Wright will talk about advanced geophysical classification, lessons learned at former Camp San Luis Obispo in California. His presentation will be followed by a brief Q&A session. Second, Mr. John Jackson will discuss risk reduction utilizing advanced geophysical classification at Fort Ord, followed by a second brief Q&A session. Then we will conclude with Mr. Doug Maddox from EPA, who will provide his perspective on advanced geophysical classification for munitions response. We will wrap up the webinar with an interactive Q&A session including all 3 speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions well in advance of that session. On this slide, we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen, or you may call into the conference line. If you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. And with that, I would like to introduce Dr. Herb Nelson, who has been serving as the CERDUP and ESTCP Program Manager for Munitions Response since 2007. Prior to that, Dr. Nelson was a research chemist at the Naval Research Lab in Washington, where his work focused on the detection and classification of buried UXO. Herb?
Thank you, Rula. I'd like to join Rula in welcoming you all to our session today. And as she said, I'll just give you a few brief introductory remarks. As most of you know, or certainly as many of you know, we are really made up of 2 programs. The first, CERDUP, which stands for the Strategic Environmental Research and Development Program, is an R&D program. It's now coming up on its 15th year and is really focused on DoD environmental problems, but at the R&D stage, as the bottom 2 bullets show you, both advanced technology development and fundamental research. The companion program, the Environmental Security Technology Certification Program, is the demonstration validation program, where we take the results of those CERDUP programs and other technologies not developed by CERDUP, transition them out of the lab into a DoD site, and the output of these programs are called a cost and performance report, where we measure the improvement in cost, or the hopefully less cost, and the improvement in performance. So both of these programs are very valuable to the DoD. We organize ourselves inside these programs into 5 program areas: energy and water, which only has an ESTCP component, and then the other 4 which have both CERDUP and ESTCP. And as you can see, these comprise environmental restoration, which is traditional chemical cleanup, munitions, which we're going to talk about today, resource conservation and climate change, and weapon systems and platforms. So let's focus on today's topic, which is the Munitions Response Program area. We have classically, meaning for the past 15 or 20 years, had a large program on munitions on land, which is really coming to an end, and that's the point of today's webinar. And then over the last 5 years or so, we've really started to grow our program in munitions underwater. Those of you that have attended or listened to the last several munitions response webinars in this series will realize that they were mostly focused on underwater work, and they were mostly focused on development and research into this, so much more CERDUP character. We've really moved through CERDUP now into land project, and we're at the end of our ESTCP effort. So today's sessions and the two talks today are focused on much more ESTCP level work and really what we have learned from the very beginnings of actual use of these technologies. So as Rula said, we have two more webinars scheduled for this calendar year, one coming up on the 3rd of December and one the 17th. We then take our holiday break and we'll be back in January, so please be looking in your on either our website or in your email box for the January topics, which will be announced soon. And of course, any of the past webinars can be accessed through the link shown on this final slide. Today's will show up after some small delay for editing and preparation, but all of the ones, the MR and all the other areas show up at this link. So with that, I'd like to hand it back to Rula to introduce the first speaker.
Thank you, Herb. And it is now my pleasure to introduce Mr. David Wright, who is a Senior Munitions Response Geophysicist with CH2M. Doug has over 25 years of experience in airborne, ground, and marine geophysics, and has spent the last 14 years adapting geophysical techniques to the UXO detection and discrimination problem. Doug is the technical lead for CH2M's geophysical classification technology development, and he is engaged with ESTCP in the development of formalized quality management procedures for geophysical classification. Dave received his bachelor degree from the University of Guelph in 1984. And with that, I'll turn it over to you, Dave.
Thank you, Rula. Today, I'm going to give a talk about utilizing advanced geophysical classification for a treatability study at the former Camp San Luis Obispo. I'll start with giving a quick background. Then we'll talk about our approach to detection and provide classification results, and then focus on lessons learned with an emphasis on our approach to QC and some of the QC lessons learned at the site. As a little background, advanced geophysical classification is simply a technology that utilizes these advanced sensors to derive intrinsic features related to the target of interest, and these intrinsic features are the principal axis polarizabilities. We call them betas because it's a lot quicker to say that. And these are related to the object shape and composition. So for a cylindrical object, you would find one larger beta, and two smaller but equal betas. Things that aren't cylindrical would not have the same feature. The other thing to point to make is that targets that are thick-walled, as munitions are, have these betas that extend out in time. This is the time along the time is on the bottom axis on this chart, right here. And so thinner walls would decay much quickly and have betas that don't extend as far. So we can use those to reject things that are obvious clutter. This technology has great potential for savings, but the potential for savings really is site-specific, and it depends, large part on the ratio of targets of interest versus non-TOI, what types of targets of interest we're looking at, and the cost per dig. But generally, the general case is we're expecting to see about a 50% reduction in costs. To go with this savings, we have to understand that using this technology is a new paradigm. We're going to leave metal in the ground. Therefore, the planning required for this technology is a little more detailed, as is the formalized quality management and reporting requirements. And to get stakeholder buy-in for using this technology, all of this process has to be transparent as well. And we need to involve stakeholders at the start. At San Luis Obispo, we did a treatability study. The camp is shown here, shown on the left panel relative to the town of San Luis Obispo. And on the right panel, we show the area that we worked at. It was 7 acres, mainly grassland. It was on a rather steep hill, and we had variable anomaly density throughout the site. As I said, the planning was extensive. Here, I'm not going to go through and name all the people, but we had 6 different organizations involved in the planning, and everybody listed here had significant contributions to the planning of this project. We also developed kind of the forerunner to what is now called the Geophysical Classification for Munitions Response, QAP, and that was implemented at this project, where we provide the project objectives, measurement quality objectives required to meet those project objectives, and then responses to QC failures and reporting requirements. Our objective at Camp San Obispo was to find the equivalent of a 37 millimeter projectile at 30 centimeters depth. We did some advanced work. We knew what our noise levels were, and we knew we could model what the response of the 37 millimeter is, and so we were able to determine what our detection threshold would be when we use amplitude response. And that is shown, that analysis is shown on the left side here. Where we have on the bottom axis we have burial depth, and on the side axis, the vertical axis is signal in millivolt amps. And that equates to different depth for different targets, obviously. And so on the right panel we show what we call a vertical conceptual site model, where we have the targeted detection depths for various ordnance items at the site. We performed the survey by basically mowing the grass with the instrument shown in the picture, and the results are presented, these amplitude response results are presented as a false color image. And here we blow up one of the operational grids to show you the various target densities that we see through the site. And we end up with over 18,000 anomalies using the detection threshold indicated 1.5 millivolts. Now, a portion of the site had very dense, was very densely saturated with anomalies, and so we were not comfortable trying to perform classification with that many targets, that density of targets. So anywhere outside of, I think it was roughly 4,000 targets per acre, we excluded from the treatability study. Okay, as the data I just showed previously were amplitude response target selection, and that is very similar to what's been conventionally done using EM61, where you have a vertically coupled transmit coil and a co-located vertically coupled receiver coil, and you just measure the response as you go along. And we did the same thing initially on this project. The disadvantage of this approach is that to detect targets that are very deep, as shown here, our target of interest at 30 centimeters, we end up detecting a lot of targets that are much smaller but shallower, and but present the same, will exceed or the detection threshold we had. So we end up with a lot more detections than what we really would want to see. So our teammates at Acorn proposed that we could use advanced detection for this project. And advanced detection is a process whereby we use all of the data in these new sensors as opposed to just the monostatic amplitude response signal. And so on the left-hand panel, we see for each transmit event there are 12 receiver coil events, measurements. And the amplitude response only uses one of those, where advanced detection uses all 12. The advantage of this is that we get increased signal to noise. So the charts on the right, if we look at the middle panel and in the bottom panel, we see the increase in signal to noise for detection using advanced detection for targets that are buried deeper. So advanced detection is actually a four-step process. The first step, they go through the site. They look at all the data. They take a 1 by 1 meter window, and they step through the site at 0.1 meter intervals, good nodes. And they invert looking for evidence of a dipole or something, a metal object in the ground. And the fit coherence, or how well the observed data fit the model data. If there's a metal object, that number goes up significantly, and we use that as the initial detection metric. So we end up with regions that we call dipole detection areas, and then we go back through each of those regions and we perform a much more computationally expensive process whereby we do a 1, 2, and then a 3-source dipole fit routine to actually find the targets, the sources, and also we derive the intrinsic features relative to the sources. In the third step, we look at those intrinsic features and decide whether the object is large enough and also has thick enough walls, has a long enough decay for it to be considered a target of interest. And if it doesn't match both of those criteria, we can reject it as being not a possible target of interest. And then we're left with a bunch of targets that are possible targets of interest. And then, so the fourth step would be simply to merge the co-located sources to get our final list of advanced detection targets. The advantage of advanced detection are the first thing, it rejects obvious clutter, as I've described, and our deeper depth of investigation, as we've shown earlier. But the other advantage we found is that we're easily able to find sources that are close together that might be otherwise hidden using amplitude response. So in the chart below, I'm showing the right here, that black crosshair is the location of a seed item, and the circle around, black circle around it is the distance that we need to have a detection within to meet the measurement quality for detecting our seeds. So this would be if we used amplitude response, and of course the red circles or dark red circles are amplitude response selections, and you can see there isn't a selection within the MQO, and so that would require a root cause analysis and corrective action. And what we would probably end up having to do is go and manually select every lobe as additional targets to make sure we didn't miss a target that was hidden by an adjacent signal. Using advanced detection, we are able to actually, the advanced detection found the 2 targets that were both there and has a very precise location for the actual seed item. That's a significant improvement for us as well. So we went from the detection phase to classification, where we had roughly 16,000 amplitude response targets, reduced those to 6,400 advanced detection targets, and then went out and took static measurements over all of them to perform our classification. And what we show here on the right-hand side is just some of the reporting images that we use to monitor the data doing these periodic tests. We test at an IVS at the start and end of every day, and we make sure we derive the correct positions of our targets in the IVS, and we also make sure that they match to the library property so we get the appropriate decision metric from our buried items at the IVS. And then on the top panel, that simply shows the function test that we do, where we make sure that all the components of the instrument are operating properly. So we went from, again, about 16,000 amplitude response targets to 575 excavations that were required, plus training digs. And I think training digs were about 150. So it's a significant reduction in the effort to recover items. We did recover 169 targets of interest. Most of them, other than 3, were QA seeds and QC seeds. One of the 3, we had 1 UXO that was recovered, and there's an additional 3 shapes that were close enough to being that could have had hazardous material in them. So, and on the right-hand panel, I'm showing what we call a rock curve, and this is what we use to assess our results. If we go down our prioritized list that we provide, if the dig results recover a target of interest, we would add 1 to the vertical axis, and if it recovers a non-target of interest, you add 1 to the horizontal axis. So a perfect classification would go straight up the vertical axis until there are no more targets of interest, and it would go straight across. And obviously, no classification would be this diagonal feature. So what we do is we provide a cutoff threshold. The analyst says, okay, beyond this in our prioritized list, we don't think anything after that is a target of interest. And what we'd like to see is a nice flat line both before and after that threshold to confirm that there's no remaining targets of interest, or at least indicate that there are not. Just a quick review. Because of the reduction in number of digs, we estimate that about a 73% reduction in the field costs for SLO. And this is not necessarily a reduction in the total project cost, but just for the cost of the field activities. Okay, so I'm going to talk a bit about our lessons learned, and we'll go through with some examples. So the first lesson learned is that effective and transparent internal quality control is critical to success. We have to, every site will have some quality issues. We have to catch them in a timely manner. We have to make sure maintain the confidence of our clients and stakeholders, and we have to advance the state of the art by making sure that these same mistakes are avoided. So I mentioned we're going to talk about some QC challenges. I call them successes, not challenges, because the fact that we're able to catch these things with our internal processes provides a lot of confidence by our client in our ability to monitor ourselves and perform these things properly. So the first QC challenge we found was a QC seed that was not identified in the classification process as a target of interest. And on the panel on the left, I show the original case where we have the square that you see is the actual footprint of the TEMTAD sensor itself. The red circle is the merge location of all of the sources there. Those are the black crosses. And the triangle is, of course, the missed seed. Now what happened, the red circle was close enough to the seed that we didn't ring any alarms in terms of detection. But because when they put the TEMTADs out, it was slightly offset from the actual target, when they did the static measurement, the seed wasn't under the footprint of the sensor, therefore it wasn't classified properly. So when we looked at this in the root cause analysis, we discovered that perhaps merging sources that were 0.4 meters apart was too aggressive, and we reduced that merge to sources that we only merged 0.2 meters instead. So on the panel on the right, the green circles are the results of the targets after reducing the merge distance. And we looked through, and any target that wasn't that we had that was not covered with the footprint, we went out and took a second measurement, and in that manner corrected this problem. We had another challenge where during the dig program, they recovered an object that we thought should have been a target of interest. It was much too small. So this was caught by our QC geophysicist going through the dig results and comparing them to our predicted results. The root cause analysis revealed that there was some imprecision in placement of the reacquisition flags, and the seed was outside of, we dug to a 0.4 meter dig radius, and the seed was just outside of that. So we had to go back and correct the procedure they were using and review the locations that they used, and reflag and reinvestigate targets that were improperly flagged. Another challenge we found was when we compared our recovered QA targets, QA seeds, we compared their positions to our predicted positions. They were outside of a measurement quality objective of 0.25 meters. Now this, when we did that with our own QC seeds, we didn't have this problem. So a review of what happened, it turns out that the procedures for measuring the QA seeds were flawed, and that was where the error was. So in effect, there was no problem with our data and no corrective action required, other than we need to make sure we capture something like this even in the lessons learned for future targets, for future investigations. So moving on with the lessons learned, the one we've seen here, we had two cases where the problem was due to imprecision in measuring locations. And so clearly we have to make sure that all of our positioning is as precise as it needs to be for this, using this technology. And thing to note is a lot of people that are doing this measuring are used to doing it the old way, and they're not familiar with classification. So they must be retrained at the start of the project to make sure that we have the precision required. Another lesson learned is that the QC documentation requires an extensive effort. Every measurement we take, for every target we leave in the ground, we have to document that all of the measurement quality objectives were met. We have to make sure the measurement we're using to say we can leave that in the ground is valid. And so there's 10 or so measurement quality objectives for each measurement. Then the measurement has to be bracketed by periodic tests. There's 6 or so MQOs for those tests that have to pass. And then there's a project level verification. That's things like making sure we collected data over all the targets, making sure that all of the seeds were identified properly as targets of interest. So you have to track all this information and make it available so that any given target you can look at and make sure it passed all the MQLs. Another lesson learned was that we need to, part of the process involves using what we call analyst calibration digs to provide some initial feedback to the analyst, some ground truth, to make sure that his library is correct and the threshold he's using for the decision metric, this cutoff threshold, is correct. And so we actually sent a crew out, we did the digs, and then they wanted to keep digging, and that caused a little grief for us. It'd be far better to actually do those digs early and come back and look at what the data is and make sure you've incorporated it properly before you provide the final prioritized list for the dig team to go and prosecute. And then the final one, I think, is that the early and detailed involvement of all the interested parties is a blueprint for success. I mean, this provides a comfort level for all of the stakeholders. You're going to run into QC issues. They are inevitable, and if you have a transparent process and are communicating properly, the project can still be a success, and you don't get bogged down with problems. So in conclusion, obviously advanced classification has great potential for savings, but it is a new paradigm, and the planning requires more effort. Quality management reporting requires more effort, and the process needs to be transparent, and we need stakeholder involvement right from the start. So here's our team again, and as I said, everybody listed on this team provided significant contributions to this project. So that's my presentation, if we have any questions.
Thank you, David, for a very informative presentation. I would like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We have received a number of questions that I'll be posing to you, David. Can you please tell us if advanced detection is always the preferred alternative over conventional detection approaches like EM61?
Actually, no. There's a trade-off. It's more expensive to perform, and so if you have a site that is sparsely populated with anomalies, you're better off using EM61 and just detecting them in that manner, because you're not going to, the savings in reduction of acute investigations doesn't pay for the extra expense of using this technology.
Okay, another question. We assume that this advanced geophysical classification methodology does not work on highly saturated areas. Can you please discuss some of the limitations of this technology?
Yeah, I think basically it depends a lot on what your targets of interest are and what your clutter is. If there's a huge discrepancy because a lot of small frag and looking for very big things, you can work in a more densely populated area. But generally, we have a cutoff that we've empirically derived at about 4,000 targets per acre, and that's the cutoff we've been using.
Thank you. Can you please provide an approximate target density per acre where advanced classification is no longer viable?
Yeah, I think that's about 4,000, 3,000 to 4,000 targets per acre.
Thank you. When you narrowed down the merge from 40 to 20, how many more targets did it add by ROM percentage?
I think it added, it wasn't that significant. It added probably, if memory serves me, about 200, a little over 200 more measurements that had to be made. So 200 out of, I think we measured 6,000. So not a large percentage.
Thank you. You noted the importance of stakeholder involvement early in the process. What approaches do you recommend as most effective for engaging and informing stakeholders?
Well, I think what we did, we had the TPP process where you meet and do the advanced planning, and stakeholders were present and involved in the process right from that start.
Thank you. If you have two potential MEC items very close and or on top of one another, how do you ensure that the fingerprint or signal you get will be correct?
We use a multi-target solver that does a pretty good job of discovering two different targets, even when they're on top of each other. They, in this project, they put two of the QC seeds were, actually I can go back to the slide if I can find it, the results. Here, I mean, these last two targets on our prioritized list were targets that they actually had QA seeds that were on top of each other, two in the same hole. So it degrades the fit a little bit, but we're very conservative with our cutoff threshold, and therefore it captures it.
Great. Thank you so much, David. We're going to come back to you later with additional questions, but it is time to move to our next presenter now. So with that, I'd like to introduce our second speaker, Mr. John Jackson, who is a geophysicist with the U.S. Army Corps of Engineers in Sacramento. Since 2011, John has served as the U.S. ACE demonstrator for multiple ESCCP advanced geophysical classification demonstrations, including the one you'll hear about from him today. More recently, he has worked to develop appropriate QA/QC procedures to be used on all future advanced sensor contracts. John completed his BS and 2 years of graduate coursework in geophysical engineering and geophysics at the Colorado School of Mines. And with that, I turn it over to you, John.
Thank you, Rula. And thank you, Dave, for doing all the hard work presenting the introduction to this technology. So for those of you over the last few years who have followed the progression of this advanced classification program, either through the ESTCP, NAOC, ITRC, or even the Corps of Engineers outreach opportunities like the M2S2 webinars, you've probably noted the emphasis on cost savings through removal actions, and that's more or less what David just walked you through. But on a lot of these general overviews, there'll be an additional slide or maybe just an asterisk that mentions something about other beneficial uses. Usually there's a list of potential advantageous uses along the lines of can be used during remedial investigations where there's biological restrictions, potential evacuation issues, and then there's another, or et cetera. And the M2S2 over the past couple of years have shown you some case studies on remedial investigation biological studies, 29 Palms, West Mesa for the evacuation issues. But today I'd like to take you through a case study on one of the others, or et ceteras, and this is basically a case study in risk reduction. So my talk today is split into two primary parts. First, we'll walk through our cry for help at Fort Ord to ESTCP and their attempt at helping us with a live site demonstration. And then the second part, of course, is taking ESTCP's work forward into the actual production project through this risk reduction activity. So here at Fort Ord, we have a almost annual prescribed burn. There's two purposes for this prescribed burn, one of which is the obvious safety benefit that assists in surface clearances. But the primary reason is actually to help maintain the natural habitat. Apparently, fire is the natural catalyst for regrowth of the native manzanita. The central impact area of Fort Ord was split into multiple burn units to assist in the burning process, and two of the central impact units ended up being labeled Units 11 and 12. Units 11 and 12 were originally planned to be burned in 2011. However, during that surface sweep in preparation, there were some large unexploded ordnance or mech items found. Specifically, there were two 8-inch projectiles that were found, which weren't necessarily expected. And due to the large hazardous fragmentation distance and the sensitively fused nature of these items, the safety office at the U.S. Army Corps of Engineers canceled the burn until the area and safety concern could be further understood. In the meantime, the only activities allowed in Units 11 and 12 were vegetation removal, surface mech removal, and then DGM survey via EM61 towed array. The burn was rescheduled for this fall, 2015. I think we're still waiting for it to happen, but the caveat was that it would have to be deemed safe by the safety office prior to burning. So as I said earlier, this is where I came in and issued a cry for help to ESTCP. At this point, my understanding in the live site demonstration program, they weren't necessarily looking for just any old site. They had shown enough successes, so they were looking for a unique scenario. Fortunately, Fort Ord presented this unique scenario in that it's not just a simple removal action, and furthermore, we offered high anomaly densities, and there were a number of questions on that in Dave's presentation, and we wanted to help answer those questions with empirical data from the field. So we wanted to actually test the limits of the current technology. So I'll walk you through the demonstration. First, we had to develop objectives for the demonstration. At this point, we had a guess as to the thermal gradient in the soil during a prescribed burn, but we didn't have all the data to make a formal statement. As such, two primary objectives were developed: detect and classify all large munitions to 2 feet, and detect and classify all large munitions to 4 feet. And the differentiation, of course, is that depth. Since we were feeling greedy and we had ESTCP's ears, we developed a second objective and asked for the world: detect and classify all munitions. Specifically, as you see here, the 40-millimeter projectile was called out, and that was due to language in the record of decision stating that high-density 40-millimeter areas would be under potential consideration for a special case scenario. So we were specifically interested in 40-millimeter performance. So first, we split up the site into 4 separate sectors. Because we weren't sure where we might incur failure due to the high anomaly density counts, we wanted to make sure we covered the full range of anomaly densities. As you can see from the EM61 data on the left, as you head west in Unit 12 to east in Unit 11, the anomaly densities increase. The approximate densities range of the sectors we selected anywhere from 2,000 anomalies per acre to well over 4,000 anomalies per acre. As you see on the right, in each unit there was a 1-acre sector and a 1.5-acre sector. They were further divided into 100 by 100 foot subgrids. Each sector was 100% dynamically mapped with a metal mapper. Afterwards, a subgrid, those are outlined in blue on the right, was selected, and each anomaly in that subgrid was queued and later intrusively investigated to provide the complete ground truth for the post-analysis. Outside of these subgrids, only the potential TOI from the dynamic processing were queued and intrusively investigated. So we had an interesting combination of dynamic and queued approach here. The first step was to analyze the dynamic data. I should point out that one of the early tests was to assess different lengths of time decay settings during dynamic collection. The standard 3 milliseconds was quickly deemed not good enough in these high densities. So the dynamic collection was extended to 25 milliseconds, which of course made data collection very, very slow. But here you can see what we gain from these later time gates. If you look at the top right corner, the data becomes much cleaner at longer time gates. This might not be advantageous for the secondary objective for detecting all TOI, but the primary objective of locating large munitions, this appeared to be a solution that could help us be successful. This also led to the concept of extending the queued collection to 25 milliseconds, and I think it's actually closer to 23. I keep saying 25, but I believe it's actually 23 for those of you taking notes. And I also like to point out this beautiful picture at the bottom of the slide. I've seen this in many, many presentations, and I wish I knew who to specifically credit, but this is somebody from CBI took this photo, and I should have copyrighted it because I think Geometrics should use it for marketing. So moving on to the queued data, it was important to determine if the primary objective could even be attempted to be met. The best way to determine this was through analysis of test pit and IVS data. So here we have a series of measurements over IVS-4, which was a large ISO buried at 75 centimeters. As you can see, all the polarizabilities are cleanly inverted, and they're pretty repeatable. Moving deeper to just beyond 3 feet, the repeatability begins to drop off a bit, but the signal strength is still clean enough to make a good inversion with positive classifications. And then moving down to 4 feet, the response isn't really repeatable, and while classification might potentially be possible, it's not anywhere near the high confidence level we would like. Post-analysis from some of the black tusk processors seems to suggest there might be a secondary target in this IVS that's causing some of the noise issues, but that's yet to be determined. So let's take a look at the rock curves. Dave introduced this concept, but here I'm showing an initial rock curve. This is this particular analyst's initial TOI list, and it's near perfect for the primary objective, which in this case was defined as all large munitions down to 4 feet. Unfortunately, it wasn't quite perfect. It looks like there was one large munition missed and errantly classified as non-TOI. Now keep in mind as we move to the next slide that this information at this stage is unbeknownst to the analyst. This is something we know on our side, and so he or she made revisions to this classification process based only on his training data and further processing. So after revising the TOI list, it looks like there was some additional training data and what appears to be some additional analyses. The rock curve does become near perfect in that no TOI were missed. They were all correctly classified as TOI, or targets of interest. And in fact, not only does the rock curve go nearly straight up, but the difference between the blue and yellow dots there, it suggests threshold criteria might have even been too conservative because there's a ton of digs past the stop dig point. And on this slide on the right, I'd also like to point out that all large TOI were classified as large TOI, which is important to us as we move forward in explosive safety. So what about the secondary objective? Well, not quite as good. There were a total of 11 missed TOI, but the good news is over half of them were actually smaller than a 40 millimeter projectile, though there were some 40s included on this miss list. This isn't the final rock curve. There's still an opportunity to revise it, but the analysis is still in progress. So at this stage, I'd like to point you out to the ESTCP report on the website when it comes out. So what did we learn from all this? Well, our primary objective was easy. I should probably caveat this statement with nothing in this realm is easy anymore, but in the realm of not easy, this objective was easy. The primary objective of large TOI to 4 feet appears difficult but potentially doable. My personal opinion is a larger, more robust data set would be necessary to quantify this statement further. Unfortunately, the secondary objective was not possible. The anomaly densities were just too high. As we move forward in the analysis of this ESTCP demonstration data, I'd like to look more closely at the depth versus signal strength versus anomaly density and come up with a similar rule of thumb that we came up with at San Luis Obispo, which was roughly 4,000 anomalies per acre, and then determine if any quantifiable statements can be made at Fort Ord. On the other side of the house, I'd like to suggest that as we move forward at Fort Ord and other difficult sites across the country, we need to consult with the stakeholder community and determine if true removal actions are necessary or if risk reduction will provide enough risk mitigation. That's obviously not a question we'll answer today, but I think it's one we should all keep in the back of our minds as we move forward. So what about our prescribed burn? The ESTCP demonstration only took us halfway, so now we have to do the real work across the other 500 acres. After the ESTCP fieldwork, our informal consultation with some forest fire researchers from the Forest Service confirmed our initial hypothesis that the temperature gradient below a foot is negligible. So this led to a creation of two zones. An outer zone nearest the firefighters, helping to control the burn, where we added a 1 foot factor of safety to this 1 foot concern, and then the inner zone where only really it's the potential flight path of the helicopter that was of concern. So visually, this split the site as so. The roads, looking symbols on the perimeter of units 11 and 12 are the fuel breaks. This is where the firefighters would be standing during the controlled burn or the prescribed burn. The yellow-colored area is the outer zone where depth of concern is 2 feet. The green-colored area in the inner zone is where the depth of concern is 1 foot. And all of these blue dots were the anomalies selected to be cued from the EM61 data. Thanks to the published NRL curves for the EM61 instrument, and then of course some additional work done from Black Tusk on the data during the demonstration, it was determined that large anomalies could be selected from the EM61 for cued data locations. So we used those values. An additional level of conservatism was added, or I guess in this case subtracted from the millivolt threshold. And the final result, or anomaly counts, are in the bottom right-hand corner in that table. The total number of anomalies based on the EM61 data that would require queuing with the metal mapper was 4,625. So, of course, using the new beta draft GCMR QAP as a template and the Camp San Luis Obispo QAP as a template, we knew we had to seed the area appropriately with both QC and QA, or what's now called validation seeds. The distribution's a bit hard to see here, but it was spread across the site. We tried to cover easy and hard areas in terms of density and terrain and depth. Another interesting aspect of the blind seed firewall plan was that it was determined the EM61 data should be kept blind from the data processors at NAVA. Since the EM61 had been collected prior to the queued work, it would be obvious where the seeds had been placed, so that was of concern. As an additional level of precaution, though, I had a rare opportunity to perform a type of QA seeding I'd never done before. During a previous field effort, a number of subsurface investigations had been performed. This was unbeknownst to the current contractor. So a selection of those holes were reseeded with inert munitions, which guaranteed they would be selected from the M61 data without artificially adding new anomalies. So I give myself the Creative Seeder of the Year award on this project, though I'm sure the project team has a different term for me. The process here was pretty standard, what you've heard David talk about in the previous presentation or other presentations on other sites. However, I'd like to point out one unique opportunity the processors had here, which David had mentioned as a lesson learned, but because UXO techs were already on site, the data processor was able to ask for training data and immediately received feedback so that she could revise her library and her selection threshold. Excuse me. So there were a total of 22 calibration digs that were selected. This resulted in 3 new library additions for TOI and 18 other munitions to the non-TOI library. And Another point I'd like to make on this slide, which I think I forgot to mention earlier, is the standard metal mapper library was not usable for this project. The one that comes with Geosoft was built around the 8 millisecond time to gaze as opposed to the 25 millisecond we were using for this project. This led to the need to develop a site-specific library through the test pit, IVS, and field data. So the classification process was also straightforward and mirrored the demonstration in this case. One unique feature was an addition of a new category of can't analyze. The can't analyze category is necessary to include the must dig anomalies where data just wasn't good enough for some reason to make a determination of TOI or not. There's a multitude of reasons why it might be can't analyze, but some of the normal reasons are unreliable data, failed inversions, poor fit coherence. But for this project, an additional category was added for the high chi-squared values. Generally, the fit coherence is normalized so that high signal amplitudes provide a similar fit coherence as low signal amplitudes, but the chi-squared fit is not normalized, and as such, it will give a good approximation of when signal amplitudes are just too high to allow for a high confident inversion and classification of the data. As a side note, I should probably say that if we had provided the M61 data, you probably could have made a similar determination with that data where the anomaly counts or the amplitudes were just too high in the M61 data. You might just draw a polygon. But since we didn't do that, we came up with this alternative methodology. So the next step was the final classification step. Why did we even need a final classification step? Well, relating back to the UFP QAP world, it was originally decided that the less than 5,000 queued targets we had could be one deliverable unit, even though it covered a large acreage. But once processing got underway, we quickly realized that in terms of data management, it was easier to process QC and QA smaller preliminary lists, and these smaller lists ranged in size from about 1,200 to 1,500 targets. This allowed for us to check the measurement quality objectives, the seed results in much more manageable bunches, but we still wanted to hold off the cluster analysis until the end with one combined database, and it might have also resulted in additional calibration digs, but I think in this case it did not. So once another opportunity here is once the preliminary dig was past the QC and QA, it was passed on to the dig team, which allowed them to get started digging, and then the dig results could also be included in the final classification process. And it's important to note here, this didn't mean any TOI were being removed from the dig list, especially since in this case they had likely already been dug. But it did result in additions that included a number of high chi-squared can't analyze digs and a small number of good library matches that had been inverted to a position well outside of the metal mapper footprint, but actually were high confidence matches to TOI. So here's the moment of truth. Of the 589 anomalies that were classified or labeled as TOI or can't analyze, there were 302 TOI, actual TOI recovered in the intrusive investigation. More importantly, you'll note that there's 2 HE 8-inch projectiles that were found and removed, and then 17 155 projectiles that were deemed mech. You'll note the large number of 155 projectiles that were ultimately deemed MD. This was a result of the shrapnel round, or the shrapnel version of the round, being left behind fully intact, but not with the explosive component. Unfortunately, our advanced sensors do a really good job of classifying the shape of metal, but they don't yet determine if it's filled with explosive content or not. So what about the non-TOI? Well, believe me, it is very odd to label actual mech as non-TOI, but based on our objectives, that was the case here. I think the large number of smaller munitions on this list gives weight to the fact that we were using conservative thresholds throughout the classification process. As a side note, when plotted, these results immediately line up with our conceptual site model for the area. The large number of 81 millimeters you see here were found in what we informally call at Fort Ord as Mortar Alley. Another side note, and please don't try and do the math on these TOI and non-TOI numbers as we walk through. There were a number of holes with multiple munitions or TOI found in them, so I'm hoping we can clarify that and make it much clearer in the final report. So here are the final numbers, the summary. From the simple EM61 detection threshold approach, there is an immediate 99% reduction in anomalies required for queued investigation. From there, an additional 85% reduction occurred due to the classification approach. This 85% number does include the verification and validation digs. As Dave suggested, in order to be in compliance with the site QAP, verification validation digs were necessary to assess the thresholds and ultimately the data usability. Fortunately, none of these resulted in additional TOI. The odd number of 99 that you see here was added as a result that the conservative approach, we already had a number of verification digs. In fact, I think the last TOI meeting our objective was actually ranked at about 418 on the TOI list. Finally, of course, here's our rock curve showing, visually depicting our success. The analyzer training and calibration data is at the beginning of this list in gray. The category 1 is in green. Category 2 is in yellow. And then the verification digs that were added at the end are in red. So I'm not quite as generous as Dave in naming specific people, but let me assure you there were many, many individual people involved in the success of this project. Honestly, with the high number of really smart people on the project, the less impressive feat was the geophysical success, and the more impressive feat was that with so many bloated bureaucratic entities, we actually were able to communicate well with each other and work as one under the pressure of a tight time window. So I'd like to take this opportunity to thank all that were involved. And I think that's it.
Thank you, John, for a great presentation. We've received a number of questions. Have you collected metallic anomalies from the site where large UXO were found? And if so, what would be a typical range of sizes for metallic anomalies in shallow depths of the site?
Yeah, we've collected a number of metallic anomalies from the site. The range of sizes are anywhere from really, really small pieces of fragmentation or other debris all the way up to 55-gallon barrels or target type features. The typical range of sizes, honestly, Fort Ord is very, very unique in that it doesn't follow what I'd call the vertical CSM for other sites. Normally 99% is in the top half foot. Say at Fort Ord, it's closer to the top foot or two where you hit the 99% number. So we've got a wide range, which makes the site very, very difficult.
Thank you, John. Now, we heard from Dave that high-density areas are better suited for dynamic detection surveys using advanced sensors. Is there a reason an EM61 was used here instead?
Multiple reasons, actually. The primary reason was that the EM61 survey had already been done. There was an evaluation of the EM61 data, and it was determined that it was of pretty high quality. We use a 2-foot line spacing or lane spacing out there at Fort Ord, which leads to pretty high quality EM61 data. The rate of the EM61 data collection also precludes financially the cost of a dynamic survey. But more importantly, we were only concerned with the large munitions here. And so the large munitions were very easy to target off the EM61 data. It was noted almost immediately that if we were actually concerned with smaller munitions, if the smaller munitions were our primary objective, that we would have no choice but to do a dynamic survey. And in some areas, you just can't do it. We'd have to do some sort of mag and dig or sifting type operation first, and then follow it up with some sort of geophysical activity.
Thank you. In terms of the lessons learned that you went over, what is the biggest thing you would recommend for other sites during the initial studies and evaluations at these sites?
Well, I guess if you have existing EM61 data, definitely analyze if it's good enough, and that takes some pre-work. At Fort Ord, we had some hills, and the EM61 data is not corrected or inverted for the positioning offset from the GPS and the sensors going up and down hills. So that's something to take a look at as well. Obviously, the depth and the targets of interest for your site are something to take a look at, and you should really consult with the geophysical team, and then, as Dave suggested, with the stakeholders and regulators ahead of time to make sure we're all on the same page. That's probably the biggest lesson learned across all of my projects. Thank
you. How many analyst training digs are necessary to develop an ROC?
That's an interesting question. Technically 0. You could develop a rock curve with 0 training digs. As we move forward and have more robust site-specific data sets and high-quality libraries, I would imagine we get closer and closer to 0. But I think there's always going to be an analyst wants that feel-good of, I want to verify these clusters, or I want to verify that this library matches what I actually think is what I think it is. And so I think we'll always have a minimal number of analyst training digs.
Thank you. And one last question. You mentioned that there was excellent communication among the various parties involved during this project. What do you recommend that other sites with multiple project partners to facilitate effective communication and project implementation?
Well, this is probably a lesson learned from Camp San Luis Obispo rather than Fort Ord, but something Dave didn't mention and might not even know about is prior to the development of the scope of work or performance work statement that went out, the Army, well, DOD as a whole, sat down with the California Department of Toxic Substance Control, DTSC, and sat down with Ed Walker and Roman Raga and went over the general goals for the treatability study and the remedial action objectives. And this open communication early on made sure we could develop a smart PWS, which led to an efficient technical planning process when we sat down and actually hashed out the details of the QAP. And so it's just communication. That's by far the most important aspect of all these projects.
Great. Thank you so much, John. We're going to move on to our third speaker, and then we'll come back to all our 3 speakers and add and ask you questions that we haven't had the chance to get to yet. I would like to introduce Mr. Doug Maddox, who is the EPA Headquarters Program Manager for Munitions Cleanup. Doug has worked for EPA for 14 years, but has 25 years of total service with the federal government, with additional positions held at the U.S. Army Corps of Engineers and the Navy. Doug has a BS in Mechanical Engineering and an MS in Environmental Engineering, and is a registered professional engineer. And with that, I'll turn it over to you, Doug.
Okay, thanks, Rula. So I'm going to give a little bit different perspective now, kind of just the regulatory side of things. We have been working hand in hand with CERTIP and ESTCP for quite a while now. I have to give Herb a lot of credit. Usually projects we don't have this much involvement with R&D, but they reached out early on and formed a classification advisory group, which is EPA, myself, and an RPM from Region 10, Harry Craig, had participated quite a bit, states, all the DoD services, and we really went through the rollout of this technology, selecting pilot sites, and really spent quite a bit of time over the last several years identifying big policy issues that maybe needed to be sent up to the policy groups. We weren't dealing with them there. We worked through a lot of pilot sites. Regulators at every site were involved, a lot of state regulators, some EPA, not as many, but we have been getting quite a bit more outreach. I think there were 26, 28 sites that we've been to so far. So there's quite a bit of background with this. A lot of regulators have worked through it, and I think there's a lot of knowledge base in the regulatory community now that can be reached out to by other regulators. The other good resource, the ITRC team just finished the document, TechReg document, in August. Did a training last week. It was the first training. There are a lot of fact sheets out there. That is a very good resource to look at. Another thing that I don't have on this, the Munitions Response Dialogue, the policy group that's across all the DoD services, EPA, states, federal land managers working on high-level issues, also looking at kind of the policy-level implementation issues and accreditation and other things, which I will talk about in just a few minutes. So areas of concern, the technology works, but it doesn't work at all sites. It may not be cost-effective to work at all sites. We have a lot of reservations, or had a lot of reservations in the beginning and still do, as far as qualifications and ability of geophysicists. A lot of the calls on what to leave in the ground versus not come down to that, and there's some programs in place to try to reassure folks and stakeholders that the right decisions are being made, and there's quality systems in place to catch that. QA, QC, very important, and I'll talk a bit about implementation as well. So site applicability or site team applicability. Does this technology work? Is your team ready to field this? I know David and John talked a bit about this, and I know on other webinars and even the ITRC document and all talk about technology limitations, terrain, geology, anomaly, density, 3,000 to 4,000 per acre is quite a bit. Any more than that, you're going to be having a lot of problems. Also, your mix of munitions, and how can you see those smaller munitions when they're looking a lot like frag or bigger munitions? So, how much cost savings are you really going to get from this, or do you need to use a different technology? Adequate characterization, you've got to have it. You've got to know what you expect to be there. That ties into a good conceptual site model in the beginning and starting out. This all gets into good communication throughout your project team and getting ready to move forward. Treatability study with a question mark. This is a question I've been asked a lot of times. Are regulators going to want treatability studies for this technology? I don't know. It depends. It depends on your site. It depends on the mix of munitions. It depends on your terrain, geology, all those factors. Has a similar, what I would look at if I was the RPM, and I would tell our folks to do as well, look at all the pilot sites that were done, the demonstration projects throughout this. Could that serve as the treatability study for your site? Is it remarkably similar munitions types and terrain and all that? If it's not, and if it's totally, completely different, yeah, you might have to get into a treatability study. Does this really work well at my site? It's an extra cost, but it may be worth it in the end. Accreditation. This deals with the contractors, qualifications, abilities, and how do we accept those? How do we know we're getting people that know what they're doing and there's a good quality system behind them? I could have Jordan Adelson come up from the Navy and give this talk, and he talked for a few hours. They came up with this great acronym, DAGCAP, DoD Advanced Geophysical Classification Accreditation Program. DoD did not come up with this in a vacuum. We worked through this in both the advisory group and the Munitions Response Dialogue. I think it's a great idea. We have a lot of contractors who are well-trained and the researchers who are well-trained. We have a lot that are just coming into this. So, what program is there to make sure that there's someone looking over them and making sure that they know what they're doing? And if they don't know what they're doing, there's a system in place to catch that and fix it. So they modeled this after the DoD ELAB program. The LAB program has been around forever. And we're accrediting the organization, not the individual. You're not a geophysicist and you're going to get your accreditation and go. It's your organization. Third-party accreditation bodies will be conducting the assessments. I believe there's 2 that they've selected. And again, this is enhancing confidence in the results by regulators and stakeholders. This really does help. With us, we're leaving a lot of things in the ground. This is different than the way things have been done in the past, and I do believe this is a very good step forward in accepting this technology. Quality. I'm a regulator. I got to talk about QA/QC and quality. Effective QA/QC is critical for stakeholder acceptance. I can't say that enough. We've had lots of discussions about QA, QC, verification seeds, on and on and on. You can't have good enough quality, especially with a new technology that's rolling out like this. You really need folks to understand what you're doing. You have to have corrective actions in place for QC failures. There are consequences that will be with the accreditation program for QA failures. If you miss verification seeds, you're going to have a problem. So those are great things for the regulatory community to be able to accept this technology works, and where folks aren't using it, that there will be checks in place that they can catch. Along with this, clear and specific data quality objectives are absolutely necessary. Like any other project, you really have to know what data you need to be able to make decisions that you need to make. How do we accomplish that? We're moving towards the Uniform Federal Policy for Quality Assurance Project Plans, UFP-QAP. Say it fast, it doesn't get any better. We kind of did the cart before the horse now. We have the Navy has the UFP-QAP for munitions response for the whole investigation, as well as the Army Corps of Engineers does. We decided that this would be a good time to jump into the classification-specific QAP. There are a couple efforts that struggled. We brought in the Intergovernmental Data Quality Task Force, which is actually chaired out of my office, working with all the DoD services, DOE, and formed a subgroup to work on this. Jordan Adelson is the man. He got this rolling. He is very energetic. There has been a lot of training, and there will be more training coming out. Very standardized way of doing business. If you want to minimize the amount of reviews and problems going through regulators, that's what we have found using this standard format for UFP-QAP. So implementation. The gist of it is it works. Regulators, we have been on board with using this at sites. We do need some things. We need clear, concise, factually correct decision documents on how we're going to move forward, what we're going to do. You need clear remedial action objectives, RAOs, on how you're going to accomplish your remedy. Land use controls, institutional controls might still be required. That doesn't necessarily, it's not knocking on this technology, because if you detect it, I think we do a very good job of classifying whether it is or is not a target of interest. However, we still have some detection issues. Things can be deeper than we can find, and there may be some very site-specific issues that we cannot overcome with this technology. We have worked through some of the sites working through the CERCLA process and how this technology fits in. I think we have a good grasp on that. But you really start with the end in mind, good planning, good communication throughout your project team, and that's the key to success for this. So I think that will end my very short plug. There's EPA's website. And now I think we're open for questions.
Yes, thank you so much, Doug. We have several questions for you. First, how do you fashion appropriate LUCs when metal is left in the ground?
That's a good question, and we haven't done it yet. It depends on the use of the property and the amount of clearance that has gone on. So what we will hopefully not have, when we're doing targets of interest, you should not have any munitions-like objects left in the ground. And that is a discussion to be had with your project team up front. Do you want, and we've had this discussion through the advisory group and others, do you want people digging up things, although they may be inert items, that may be munitions, they look just like munitions, and they're going to be calling EOD and responding on and on. Those are things to keep in mind as you're developing your remedy.
Thank you. Do you believe that all regulators will accept the use of advanced geophysical classification? We've been working very hard doing training, working with CertiPia CCP and other groups. We have more with the ITRC group to explain
site types that this can be used at and all. I would hope that regulators would be informed. And if this is very new to them, myself or any of the states that were involved in the ITRC can certainly steer folks towards getting more information, getting more training so they can make an informed decision with their project team.
Thank you. And one last question for you. How will regulators gain the technical capability and expertise for overseeing advanced geophysical classification projects?
Right. So two parts of that. We are doing quite a bit of training. Like I mentioned, ITRC did a training last week that was geared towards regulators, state and federal. ESTCP has a project working on developing some regulator-specific training, which I'm going to be a part of. We are also, some states have already started contracting out for specific experience with the advanced geophysical classification. Within EPA, we are also looking at our support contracts and adding in line items to allow our folks to get that type of specific support. Right now we just have mainly UXO type of support and advice in the munitions realm, and we need to add in and be able to have them access that type of information.
Wonderful. Thank you so much. And now we'd like to sort of open the floor for all three speakers to answer some broader questions. We did receive a question from a Navy end user about the appropriateness of technologies for one of her sites. And she states the following. In previous MRP trainings, presentations that I've heard, it was communicated that geophysical classification is not appropriate for use at disposal sites. I am investigating an MRP AOC site, which was identified as a disposal area. However, soil and groundwater sampling have not revealed that there has been an environmental release. A standard geophysical survey was conducted at the site, which shows over 2,000 subsurface anomalies detected in about a 3-acre area. What technology would be appropriate for a site like this? And Dave, I'd like you to take a first crack at it before we turn it over to John and Doug.
Yeah, I'm not sure. I'd like to know what the targets of interest, what do they think is there? You'd have to look at what the conceptual site model says before you can make that determination. If there's very small targets, then it's a problem. And if it's disposal, we don't know what depth they're at, so it's not clear that we would see down deep enough. So we really need to know the conceptual site model before you can decide whether it's appropriate or not.
Thank you. John, would you like to add anything to this response?
I completely agree with what Dave said. I think the rule of thumb is for disposal or OBOD type sites. This is not the recommended technology. You should be looking at mag and dig or sifting type operations. But the 2,000 number sticks out to me, and that's pretty small for a disposal type area. So I would just reiterate what Dave said, which is look at the CSM and a little bit closer and see what depths we're really looking at, and if these were individual anomalies or polygon anomalies.
Okay, if I were to clarify and tell you that the site was created from dredged spoils and contains 20 millimeter, 40 and 50 caliber items, would that help in giving a bit more specifics on the type of technology that can be used?
You've scared me away from classification even more with that description. Those are definitely in the smaller range, and whenever you're dealing with dredging, you have inconsistent depths, I would say. So I would definitely look at alternative technologies.
All right. Thank you very much. Doug, any words of advice regarding this site?
Yeah, I agree with both the previous guys. I suggest that you talk to Brian Hari at NAVFAC. Brian's been on the advisory group with us for a long time, knows classification really well, and I think he could advise you better than we could over the phone.
great advice. Thank you very much. Okay, another question for the three of you, starting with Dave. Can you please expand on whether the technologies you discussed today are appropriate for remedial investigation?
Again, that really depends on what you're trying to do. There are certain circumstances where you might want to incorporate the technology, but the problem, a lot of remedial investigations, the MD, the fragments that you find are points of interest that we need, and we can't tell with classification what the source. We can tell the shape, so we can find intact munitions, but we can't look at frag and say if that was actually due to targeting target practice or something. So it really depends on the RI, I believe, on what you're looking for. There's a case where we were looking for discarded munitions, and we're worried about how much what the effect is on the local area in terms of explosive arcs and evacuating buildings, etc. And I think there's a role for something like that. But.
John?
One of my counterparts at the Center of Expertise in Huntsville has a line of wherever you would use an EM61, you can use this technology, and I think that sums it up succinctly.
Doug?
Yeah, I think it's a possibility. It all depends on what your objectives are and if using this technology would meet them.
Thank you. We did not really discuss costs. Can you, starting with Dave, tell us a little bit about the costs associated with rolling out this technology compared to conventional technologies and approaches?
Yeah, I think there will be a lot of information that comes out that can talk to cost directly, but just in general terms, certainly these sensors are not nearly as efficient as putting together a bunch of EM61s for doing the initial detection survey. So if you want to use advanced detection, it needs to pay off in terms of reduction of the number of acute investigations you have to do. So there's some calculus that has to be performed for that. And again, areas where the cost to dig is very expensive. This adds a lot of value. And the other kind of side effect of this technology is that the actual cost to perform a dig can be considerably smaller because of the refined positions that you get. And that has, that was brought up with folks in Vieques where digging is very hard, the ground's very hard, and so having more precise position to dig actually saves considerable money as well.
Thank you. John, would you like to add anything?
Yeah, it's definitely a balance between number of anomalies in an area and what technology you should use for dynamic detection. We had done a study around this time last year that sort of gave a rule of thumb that around 500 anomalies per acre, you might want to start looking at some sort of advanced sensor dynamic detection as opposed to the standard EM61. But of course, each site is unique and each company is unique, so everybody should run their own site-specific cost analysis in regards to that. But then I'm sad that Dave didn't reiterate this again, but one of the hidden costs is this technology does require a higher effort on the QC side. And so the processing time and the time spent analyzing this data does go up a little bit, so you need to take that into account as well, that the quality control costs for each contractor will go up.
Doug?
I'm not as much on the cost end of it as I am from the benefits. You do higher QA/QC helps us quite a bit, as well as I think once you get through going through the advanced classification process, you have a much better idea of what you got and what you left behind. It can reduce the residual uncertainty a lot, and make you a lot more comfortable with your decisions. So keep that in mind as well.
Great, thank you. We have a question for Dave and John. With regards to offering and expanding these services within DoD, do you foresee additional challenges that have not been discussed for newcomers to this industry as far as gaining a foothold for using this technology and then being able to offer it to the services? Starting with you, Dave, please.
Yeah, there will be some short-term pain, I would think, because it is complex technology to utilize. But there are methods to get the training that's required, and through the accreditation process, you'll be able to prove to people you can do it. But if you don't have anybody who can do it in your company right now, there's a learning curve, and that's just the case anytime new technology comes through.
And John? Yeah, absolutely. I can speak from personal experience. The first time you look at this data, you're just overwhelmed. This isn't your 4 channels per data point instrument anymore. You're dealing with over 600 points of information, and the filtering and processing you can do with all of that information is a database management nightmare. And just from that end alone, it's much more complicated and makes your first time through very difficult. Even if you're the smartest guy out there, you're going to find yourself questioning this. So my advice to any newcomer is to get a hold of a practice data set and try it yourself a few times, and then of course we'll have the accreditation process that Doug mentioned that will help make sure that we do have qualified personnel and companies throughout the industry.
Thank you very much. And one last question before we wrap up. You heard from Herb Nelson earlier in the webinar that there are 2 components to the Munitions Response Program for startup and ESCCP, and the other component is the Marine component. So do you believe that advanced detection is viable for use in marine surveys? Starting with you, Dave.
Yeah, the marine environment adds some significant challenges. You don't see where the sensor is. So navigating, or actually steering the sensor is more difficult. Knowing where you are is a little more difficult. But I think there are systems that are being developed. I know there are systems that are being developed now to overcome these challenges. And it's not going to be ready tomorrow, but soon we'll have systems that will work in the marine environment for portions of the marine environment at least.
John?
Yeah, absolutely. There's nothing in a marine environment that precludes the physics or the concept of advanced detection. And so once we get over some of the positioning hurdles, my guess is we'll see even greater cost savings on that side of the house than we do on the land side.
Wonderful. With that, I would like to thank all our speakers for wonderful presentations, and our audience members for asking fantastic questions. Our next webinar is on Thursday, December 3rd, and it will highlight DoD efforts on prioritizing, detecting, and treating emerging contaminants. This webinar will feature 3 speakers. Mr. Paul Yaroshak from the Office of the Assistant Secretary of Defense, Dr. Jennifer Field from Oregon State University, and Dr. Patrick Evans from CDM Smith. Before we conclude, I would like to remind you that you can download a PDF of the slides from the CERDUP and ESCCP webinar webpage, and the audio will be available in about 2 weeks. You can also access prior archived webinars from the website. At this point, I would like to remind you to please take a moment from your busy day to complete the survey that will pop up on your screen at this time. And with that, this concludes today's webcast. Thank you.